This video is going to go back over the greatest integer function. It is one of the last parts of the notes we took today, and while I was driving home today, I realized that I actually did one of these problems incorrectly. So I'm going to show you guys how to do this correctly with the video, and then if you were in class with me, you can fix your notes, and if you're absent, you can just start fresh with me now. So we're going to come over here first, and we're going to read our limits for the greatest integer. Now, greatest integer is defined this way. If I choose a number, say between 0 and 1, like 1/2, and 1/2 sits right here, the greatest integer for 1/2 is 0. If I chose 1.9, the greatest integer for 1.9, which sits here, would be 1. So greatest integer works like this. If f of x is the greatest integer function, and I say find f of 1/2, I said that goes back to 0. If I said find f of 1.9, you would take that back to 1. F of negative 2.5 would take you to negative 3. So you're always going to the integer on the left side of the value that you have for your x value. So 0 goes to the left, it goes to 0, or 1/2, take it to the left, you go to 0. 1.9, take it to the left, you'd go back to 1. Negative 2.5, go left, you'd end up at negative 3. With that in mind, anything between 0 and 1 is going to have a greatest integer of 0, and so that's where this first step comes from. If your value is between 1 and 2, it goes back to 1. That's where the second step comes from, and so forth. So we actually spent some time in pre-calc graphing this. To read the limit value, I would approach 0 from the right. So coming from the right side of 0, I am here, and so that would just be 0. From the left side of 0, I would be on this step, and I would be at negative 1. From the right side of 1, I would be here. And from the left side of 1, I'm actually going to be back here, and that y value would be 0. Okay, so we have discontinuity at every integer. Now when we go and apply that idea to limits, and this is part of what you're going to be doing in your practice problems, we need to be a little bit careful. This one says we are going to find the limit from the right side of 2. And so what I'm going to do first, let's just split this up. And this first part, the line 2x, if I look at the limit on the right side of 2, that's just going to be 4. So that's no different than just plugging in the 2. But if I look at things on the right side of 2, like coming in this way on the right side of 2, that goes back to 2. So I believe that one we answered correctly in our notes. But this next one is the tricky one, and we need to be really careful about it. So I'm going to kind of give a space here for my work. I have to show two things here. Number one, I have to find the limit as x approaches 3 from the left of this function. And number two, I have to show as x approaches 3 from the right of the same function. And if they equal each other, then I'll have a limit. Okay. What I'm most concerned with is finding the limit right here, because I know the 2 doesn't change anything. So what I have to watch out for is focusing just on this piece for now. If I'm going to approach 3 from the left, so if you think of your number line, and I'm approaching from the left side of 3, I'm in this area right here. And I'm heading towards 3. So I am looking at numbers that get gradually closer to 3. So if I did a little XY table just for this piece, and I let my x's get really close to 3 from the left side, it's going to be things like 2.7 maybe, 2.8, 2.9, 2.999, etc. All right. Now, those are numbers approaching 3 from the left. When I put them in right here, I'm going to be using the negative of that value. So if I take my first one, I'm going to be looking at the greatest integer for negative 2.7. So I'm taking negative 2.7, or I'm taking 2.7 and I'm plugging it in right here. And now it's negative 2.7. So the greatest integer for negative 2.7 is negative 3. For 2.8, it's also negative 3. And all of these approach negative 3, or go to negative 3. So now I have this limit is the same thing as, let me erase this line here. The limit as x approaches 3 from the left of that function is the same as 2 minus negative 3, which is 5. All right, and then I'm going to do the same thing on this other side. So I'm going to approach 3 from the right. So I'm going to be on this right side of 3. I'm coming in from 4. So I'm going to get closer and closer and closer to 3, but coming from the other direction. So maybe something like 3.3, 3.2, 3.1, 3.01, etc. I'm going to get really, really, really close to 3. I'm going to put those values in right here, and then that's going to change them to negative numbers. And so 3.3 negative is going to be, let me erase here, 3.3 negative sits, I don't know, here somewhere. It goes back to negative 4. I always go to the integer on the left. In fact, all of these will go to negative 4. So now I have the limit as x approaches 3 from the right of 2 minus a negative 4. And that, you guys, is 6. So because the two sides don't agree, we have does not exist. Now, in class, we also got the answer of does not exist, but for a different reason. So I do want you to go back and fix your work, and hopefully with the table, this is going to make more sense. All right, let's try the same rationale on the last one. So we're going to take and look at the limit. We have to look at both limits as x approaches 1 from the left. Let's get the whole function in there. And the limit as x approaches 1 from the right. That looks a little sloppy. I'm going to fix that real quick. All right, so approaching 1 from the left, and then dividing by 2. So what do you think that's going to be? So if I approach 1 from the left, I'm looking at values in here. So 1 from the left, I'm looking at values right here. Okay. And then I'm going to divide them by 2. And then I'm going to take the greatest integer. So for example, if I chose a number like on the left side of 1, like let's go 0.8, and then we're going to go 0.9, etc. If we divide that by 2, we're going to have the greatest integer of 0.4, correct? And 0.4, if I look at where that's at, 0.4 is sitting right here, and I'm going to take it back to 0. So these all go back to 0. So I'm going to end up with 1 minus 0, and that's going to be just 1. On the right side of 1, I might have things like, let's see, on the right side of 1, I'm going to come in from 2. So I might have something like, I don't know, 1.8. Oh, let's come in a little bit closer. Let me do something like really close to, like maybe a 1.2, maybe a 1.1, something like that. And I'm going to cut that in half. So half of 1.2 is what, 0.6? And if I take 0.6 and I put it on my number line, it's kind of be like right here, and that goes back to 0 also. So this is also going to be 1 minus 0, which is 1. So we can say then that this limit would be 1. Okay. I didn't elaborate on these other x values, but if you cut them in half, you're going to be back between 0 and 1, and all of those numbers go back to 0 with your greatest integer. So I hope that explains that one, or those three. The last thing here was we talked about your notes, or talked about your practice problems today. And let me just erase some of this. On some of these, you're going to have to just do direct substitution. And if that doesn't work for you, maybe you can factor to get yourself going, or in this case, clean up your common denominator on the top and so on. On number 3, you guys had that graphing assignment that is in your notebook. So I want you to look at that graphing question that you answered. So you already made a graph of the absolute value of x over x. I want you to read that graph, and I want you to find your one-sided limit. For numbers 5 and 6, I was telling the kids that, your classmates, that when it just says to find the limit, that is understood that you have to find both the left and the right-sided limits. So for number 5, I'm going to find the limit as x approaches 2 from the right, and the limit as x approaches 2 from the left. Now, the right-sided limit is going to use this function because that's where x is greater than or equal to 2. That's the right side of 2. So this becomes the limit as x approaches 2 from the right of negative x squared plus 4x minus 2. And then you would just plug 2 in. Your left-sided limit is going to use this inequality here. So this one becomes the limit as x approaches 2 from the left of x squared minus 4x plus 6. And again, you're going to plug 2 into that. If you get the same value, then you have the limit existing at 2. When you get to number 7, pay attention to greatest integer. And when you do 9 to 10, I want you to go back to discussing continuity on your closed interval. And that means we follow the procedure in our notes, which is for this right here. So it's what we did for this problem right here with the semicircle. Hope that helps. Hope to see you guys back in class soon.